So now I just start. CA3, you didn't see till now? CA3 mark signature.
Yes, sir.
These are the answer sheets. You are in CSB now?
CSB1.
So there are three sheets for CSB, CA3, CA4 and final marks. See all the three and put your signature on it. So I am just going to share my screen. I hope my screen is visible to all of you. Please make it confirm.
Yes,
Yes, sir.
Yes, sir.
Yes, sir.
Okay. So the content that we are going to discuss for today is what stochastic process. So before that, like what exactly is stochastic process? We exactly move on that what exactly a stochastic process. There are some prerequisite. There are some prerequisite that one must know. So I will start with the prerequisite. So it is started with a random variable. The random variable is a term associated to the probability. The random variable is a term associated to a probability. So what is a random variable? It is what a numerical value associated to a random. The numerical value associated to a random experiment is known as a random variable. Now, what exactly we mean by it? So here there is a one more term which comes in the picture is random experiment. So what is a random experiment? A experiment whose output is not decided in advance is known as a random experiment. Means we can decide what is the set of output, but not exactly what will be the output after the experiment comes. Then such experiment we call as a random experiment. And what is random variable? A random variable is nothing but it is quantifying of that random output of the experiment. So we can say it is a real valued function whose domain is the sample space, and outcome is from the set of real numbers. Is outcome from the set of real number. So if I'm denoted it as R, so R is a function, R stands for random variable. It is a function whose input, that is the domain, is sample space and output is a real number. So this function we call as a random variable. Now, if I take an example to be more clear on it, so I am taking a simple example. Since we are talking about the variable, so generally it is denoted by capital letters like capital X, capital Y, or like some other capital letters. As uh, already shown to you, it is a mapping, a function whose domain is sample space and output is a real number. Real number it may be anything, it may be negative, positive, zero, fractional, rational, irrational. It may be anything depending on the random experiment. Suppose I am taking a simple example. So we are tossing two coins. So two coin are tossed simultaneously, and we are taking x as the random variable. So now when the tosses, we are doing the tosses, what will be the output? The output may be either head or tail. If it is simultaneous, we are tossing two coins. So the output or the sample space will be looks like both of them is head, head, tail, tail. So this is the sample space. Now, It's our choice that what we are deciding to random variable. As here in this example, we are deciding the random variable is the variable which count the number of heads. As we have talked about, it is a numerical measure, so it is always about the counting. So the number of heads in the experiment is our random variable. So if you see what is the possible values of random variable here, it may possible that both of them comes out to be tail. That is none of the head. So the value of random variable in this case will be 0. The second and third, that these two choice gives me the value of random variable as 1 because it is having only one head, and the first one gives me the random value of the random variable as 2. So the value of random variable in this experiment will be either 0 or 1 or 2. As you can see here, it is from the set of real number. So this satisfies the property. What is the input? The sample space. For example, if I give the input as head, this is one of the sample space. So what will be the corresponding value for this function? It will be 2. It gives you 2 heads. So this is how we can correlate it with the standard definition. This is from sample space, that is from input, and this is the output which is decided on the basis that what is your random variable. For example, if I want to decide the input or I give the input to tail and tail. So X is counting the number of heads, no heads, so it will give you the value as 0. So this is how we can decide or we can construct a random variable corresponding to a given experiment. It is decided by ourselves that what we are exactly counting in the random experiment. For example, our random variable, another I am taking as y, it may be, it is counting the number of tails. It may be, it is counting the number of tails in the random experiment. So, as per input, we can decide the value of y also. Moving ahead. Now, on the same time, we can also calculate the probability, the value of the probability for particular value of the random variable. For example, if I am talking in this experiment, so just check it. So what is the random variable value? And I'm going to make a table. So we are having random variable x is equals to x. And in another column, I am writing its probability. Probability px equals to x. This is how it will be written. So the possible value of the random variable is 0, 1, and 2. Now I am interested to find the probability corresponding to those random variables values. So the probability of getting 0. The definition of probability, standard definition, what it says that number of favorable output divided by the sample space cardinality. So what is the sample space cardinality in this example? Total 4 outputs are there. And when I am saying 0 as head, so favorable is only one event, which is tail and tail. So as per probability definition, this probability will comes out as 1 by 4. Favorable event divided by the number of event in the sample space. In the same manner, if I am interested to know what is the probability when the random variable x is taking as the value 1. So favorable event, second and third is the favorable event. So 2 favorable, sample space is 4. So 2 upon 4. That means the probability that the random variable will taking as a value 1 for this random experiment is 2 upon 4, which reduced to 1 upon 4. If I am talking about 2 upon 2, so 2 means 2 heads. So favorable is only the first case. So 1 favorable, so 1 upon 4. So this is how we can find the probability of the random values, or better to say the values of the random variable. This table is known as the probability distribution table. This table we call as a probability distribution table. Moving ahead, taking one more example, or before that, there are two kind of random variable. The one is known as a discrete random variable, and the another is known as the continuous random variable. So as the name indicated, discrete and continuous, a random variable we will call as a continuous random variable if the sample space contain, or a random variable is called as a continuous random variable if its sample space is having the values, or the values are in the continuous manner. They can be anything, not only about the integers. For example, if I am taking a random experiment which is measuring the weight of the students in a class. So weight is anything, it's not all about integer. Like weight may be 50.001 kg, 49.75 kg. So this is how, so these are not only integers, so we will call it as a continuous random variable. On the same time, if it is taking only the discrete values, only the discrete value, then the random variable is said to be discrete random variable. For example, the example that I have taken initially, this example, if you see what is the possible values of the random variable, here we are having 0, 1, 2. So they are integral values. So this random variable x we will call as a discrete random variable. This random variable we will call as a discrete random variable. On the same time, it's if it is like taking continuous values, then such random variable we will call as a continuous random variable. For example, if I am taking example of a continuous random variable, we can take it as a production, continuous production of a machine. So that can be considered as a continuous random variable. So there are two kind of random variable. One is discrete and another is continuous. I am taking one more example to be more clear on this concept. Now what it is, so a random experiment, or an experiment consisting of three independent tosses of a fair coin. That means a coin is tossed three times. Now they have decided, they have assuming three random variables. The first one is x. What it tells, it is counting the number of heads. Then y, it is counting the number of tails. And z, z is also a random variable and it is counting the length of a head run. Now what we mean by head run? A head run being defined as a consecutive occurrence of at least two heads. Its length then being the number of heads occurring together in the three cases. So these are the things. Now what the question is asking, we need to find the probability function. Probability function means probability distribution function, as we have done in the last example. So as you see, before writing the probability function in this example, this is the probability distribution function. So before writing the probability distribution function, what I need to decide? I need to decide the possible values of the random variables. So in this example, we are having three random variables. One is counting the number of heads, and another counting the number of tails, and the third is the length of a head run. So first we will decide the values, then on that basis we will try to make a probability distribution table. So now variable x is there, variable y is there, and variable z is there. So three variables are there. So what is the possible value of x? Yes, anyone, what did you think? What is the possible values of the x? It is counting the number of heads. It is counting the number of heads. So when I'm doing tossing of a coin 3 times, so it may possible there is no head, all the 3 is tail. So one possible value is 0. It may be 1 head, it may be 2 head, and it may be 3 head. So the possible value for the random variable x is 0, 1, 2, and 3. In the same manner, y is counting the tail. So the same for y also, 0, 1, 2, and 3. So these are the values of the random variable x and y. Now we will decide the value of z also. And z is a length run. And what we mean by a length run? Head run, sorry. Head run is what? Consecutive occurrence of at least 2 head. Then the length is the number of head occurring together in the 3 tosses. So anyone, what can be the possible value of z?
0, 2,
0
and
or 1.
3.
0 and 1.
0 and 1. Another is saying 0, 2, and
2
3.
and all 3.
Okay, let us try to see what it exactly. So if suppose that our output is looks like head, tail, head. Can I call it as a head run? No, this is not a head.
No.
Because it is simply explained what we mean by head run. It is consecutive occurrence of at least 2 head. So this is not a head run. Now if I am taking head, head and tail, yes, this is a head run because it is having 2 head consecutively and its length will be comes out as 2. Try to understand it, what the question is saying. Head run and its length. So in the first case, it's 0 because head run not exists, so length is 0. In the second case, its length is 2. What is the third case? The third case may be when all the 3 heads are there. So this is also a head run and the length of this head run is 3. So the possible value for this random variable z will looks like as 0, 2, and 3. 0, 2, and 3. So this is how we are deciding the value of x, y, and z. Now the question is not only asking the random variables possible values, but they are asking the probability function for these things. Now for probability function, I need to know the sample space. Since we are doing the 3 tosses, so what will be the sample space in this case? If I listed the sample space, so easy way, since there are 3 tosses, so total will be 2 to the power 3. So total will be 8 output for this sample space, or total 8 entry are there in the sample space. How to write it? It may be 4 times head, then I am writing 4 times tails, then 2 times heads, then 2 times head, and 2 times tails. In the same manner, then 2 heads, then once again 2 times tail. Now single entries, so head, tail, head, tail, head, tail, head, and tail. So this will be our sample space. Total entry is 1, 2, 3, 4, 5, 6, 7, 8. So this is our sample space for this situation. Now I'm supposed to make the probability distribution table for this. So firstly, I'm making for x. So how to write it? X equals to x, that is the possible values of random variable, and in the second column it's probability. So the possible value for x is 0, then 1, then 2, and then 3. Now probability of 0 heads. So just see 0 head means only favorable is the last output. This last output is only the favorable one. All the tail 0 head. So favorable is 1 and total is 8. So 1 upon 8. The probability that the random variable will take the value as 1 is 1 upon 8. Now I am talking about when its value is 1. So 1 head. So 1 head favorable event is what? if I'm taking one head favorable event, so this is the favorable one head only. And where is another one head? This is also favorable one head. And where else? So three head, two head, one head. This is also one head. So if you see, these three are the favorable events. So three favorable and total is 8. So 3 upon 8 will be the probability that the random variable will taking the value as 1. In the same manner for 2, now we will count 2 heads. So 2 head favorable is also 3. So 3 upon 8, and 3 is only one case, so 1 upon 8. This is the probability distribution table or probability table for this random experiment. Probability distribution table for this random experiment. Moreover, we will call this random variable as a discrete random variable because it is taking the discrete values. In the same manner, y, we can make the probability distribution table for y. So this is how it will be looks like. Y equals to y. So the same manner, possible values 0, 1, 2, and 3. In the same manner, we will make for z. So z equals to z, and then probability that z equals to z. All of you try to make a probability table for z. Y will comes out as it is, same as x. So try to make it for z. Yes, beta. All the three seats are there. CA3, CA4, and final sheets. So all of you do try to find this probability distribution table for Z. When done, you can let me know. Yes, anyone who got the values for this Z random variable, probability values?
5 by 8, 2 by 8, and 1 by 8.
For 0, it's 5 by 8. For 2, how much it is?
2 by 8.
And then finally, it is 1 by 8.
1.
So those who have done can match it. So 5 times no hadron is there, and then length 2 hadron is 2, length 3 hadron is 1. Only the first one is favorable for the third case. And for the second case, the favorable is, this is the favorable one, this is the favorable one, consecutive head occurrence. So this is how we can find the probability distribution table or probability table for a random variable x. Yes, if you are having any concern or doubt, you can ask for it. If no concern is there, we'll proceed further. Should I move forward or having any concern?
Yes.
Okay. So now let us proceed further. So as I initially told you that today we are going to discuss about the stochastic or the random process, and these are the prerequisites that one must know, that what is a random experiment, what is a random variable, and how one can construct a probability distribution table or probability table for the random variable. So now let us proceed for the random process. A random process or also we can call it as a stochastic process. So it is the extension of the random variable. So when I'm talking about random variable, generally we are counting about 1, 2 or 3 random variable. But if we do the extension of this, then we will arrive on a stochastic or a random process. A useful extension of the idea of a random variable is known as a random process, while the random variable x is defined as a univariate function. What I'm talking about univariate function means only one input is there. X is a random variable and S comes from the sample space. Random variable, we are call it as a univariate function. On the same time, a random process is a y-variate function. Please pay attention that what we mean by y-variate function. So a random or a stochastic process is a y-variate function. So it means random variable is only for one variable, only input. But if I am talking about for two, so S and T, sample space, and one more variable is known as index variable or index parameter, where S is the outcome from the random experiment and T is the index variable. Generally, the index variable is taken as time, but it's not necessary that it should be a time unit. It may be some other variable associated to the outcome of the random experiment. So here I am considering T as a time unit. So we can take that random process as voltage in a circuit over time. So now, like if I am including one more variable in a random variable function, then that gives you the concept or idea about the random process. So if I am taking X as a random variable which measure the voltage in a circuit and correlate it with the time also, then that extension we call as a random process or stochastic process. For example, at time t equal to 1 unit, the voltage in a circuit, let it be 100 units. Now, as time increasing, time t equal to 2, we will get another voltage measure, 3, another voltage measure. So it's not only output from the circuit, but also it is indexed with a time variable. So such situation or such extension of a random variable is known as a random process or stochastic process. Some author also defined it as it is the study that how a random variable evolves over time. Evolves over time. Like as time changes, how the value of the random variable is changes, that process or that representation we are calling as a random process. Now, most of the time, like I already discussed with you, it is a y-variate function, but most of the time a random variable will only denoted as x of t. No problem, we can denote it as x s comma t also, but the thing is that most of the time it is using this notation. So it means what? We are fixing the sample space s and varying the time unit t. Varying the time unit t. And what is xt? Xt is a random variable, and so we can say a random process is a collection of random variables indexed by the time unit t. A random process or a stochastic process, we can say the collection of random variable indexed by time t. Indexed by time t. Now, let us take one more example or one more definition. What it says that a random process is it is a rule that maps every outcome of an experiment with a function xta, where t is the index variable as discussed. but it may be any other index variable also. And A is what? The element of the sample space. Now I am taking two examples. This is the geometrical representation. So I am taking a random process X, S1 and T. What is S1? The input, or we can say a member of the sample space. Output of a random experiment is S1, and this is how as per time it is changing. We can take an example of a number of calls a call center is received. Number of calls a call center is received as the time t. So it may be in the morning time at 10 a.m. less number of calls are there. Then as time increasing 11, 12, 1, 2, it may the calls will increasing in the numbers. But on the same time, when we are on the downside, like 4, 5 in the evening, it may be down or it may be up. So if you see here, it's not only the number of calls we are measuring, but what we are doing, we are measuring the number of calls as time unit t. Let's suppose that this is the call for 10 a.m. Then it is 11, then 12, then 13, 14, 15, 16. So this is kind of geometrical, or better to say graphical representation for a random variable X. On the same time, for some other event S2, I'm taking some more events which are S2. So S2 means S2 is the entry from the sample space and T is the time index or time unit here in this example. So this is what the behavior with respect to time that this random process is having. So one example I have given you for the number of calls received in a call center when we are indexed as a time. It may be number of students entering in a classroom as per time. For example, 9 a.m., then 9:05, 9:10, 9:30, 10, 10:30. So this can also be counted as an example of a random process. Moving ahead. So the same example or almost same example I am taking again that I have taken previously. So here we are considering tossing a coin. We are considering tossing a coin experiment. So the output is head and tail. Now we are defining two random functions. So the first one is X. Head is the outcome from the sample space and tail is also outcome from the sample. Better to say outcome. In place of outcome, the member of the sample space. So now I am taking head with the time t and making a function as sine t. Now you may ask that from where sine t comes in the picture. So quite simple. It is decided on the basis of the nature of the values of x. So here I just decided that the number of head as per time t showing the graph same as the sine function, and number of tail is same as the cos function. So if I put t equal to 0 unit, if I put t equal to 0 unit or t equal to 1 unit, so t equal to 1 means what over here? If I'm putting t equal to 1, then what will happen? How it will be looks like? So x of 1 comma head. So it means what? The random variable which taking head as the output at the time unit 1. So it will give us sine of 1. In the same manner, if I am taking time as 2, 2 of head, then it will gives you sine of 2. In the same manner, rest of the thing. We can call it as a discrete or random variable as per the nature of the time unit that we are considering. If suppose that we are measuring time in a continuous manner, like it started from 9 a.m. and continuously till lasted, then we can say it is an example of continuous time random variable. And if we are taking time as a discrete, like firstly at 9 a.m., then 10 a.m., then 11 a.m., then 12 a.m., then we can call it as a discrete random variable example. Now, in a random variable, so if you see, this is how, and this is how the graph will be looks like. So T row 1, row 2, row 3, row 4. What is row 1, row 2, row 3, row 4? These are the entries, or we can say the inputs taken from the sample space. Like head and tail in the previous example, it may be there are more than one inputs. Like suppose that throwing a dice, the output may be 1, 2, 3, 4, 5, 6. So this is how we can check the behavior of the random variable by taking this example. Now over here we are having furthermore classification. So we are having deterministic and non-deterministic random process. So it's quite obvious, like deterministic means what? As per the given information, we can find out the future values or the values which are missing. We call it as the deterministic, otherwise non-deterministic. So a random process is called deterministic if future values can be perfectly predicted from the past value. For example, this is an example I have taken. So xt is a random variable that is taken in this problem, and its behavior looks like a cos omega t plus this zeta, where a and omega are known as the constant. A and omega are known as the constant. So from here, I can put the value of the random variable, this zeta over here, as per time index, and on that basis I can get a table. On that table, by using the least square method, we can fit a curve, and that curve can predict the future values of our random variable. So this we call as a deterministic process. If it is not like this, we will call that as a non-deterministic. So non-deterministic means what? A relation is given, but not exactly in terms of a random variable. And we want to predict the future value of the random variable. So for that, we need to use the non-deterministic process, or that process we call as a non-deterministic random process. Now two more terms. One is stationary random process, another is independent random process. So random process is called stationary if its statistical property do not change over time. Stationary, as the name indicated, not changing. So if a random variable is such that its properties, statistical properties is not changing over time, we call it as a stationary, otherwise independent. Now, what we mean by statistical property? Statistical property means what? Like the mean value of the random variable, the variance, the standard deviations, these are not changing over time, then such random variable we call as a stationary random variable. For example, generally we are saying when we are tossing a coin, there is a 50% chances that one get head and 50% chances that one get tail. But is it really work? Suppose I am tossing a coin 2 times. So as per this rule, one time I should get head and one time I should get tail. But it is not the case. It may be both the head is there or both the tail is there. So when I'm saying 1 upon 2, 1 upon 2 is head, 1 upon 2 is tail probability. So we are talking about the mean value of the head. Now what it means, what we mean by this thing. So if a toss is consecutively performed for a large number of terms, suppose that a toss is done for 1 crore times. So in that, if we see the output, it is almost 50% time head and almost 50% time tails. So if an experiment is performed continuously for infinite number of times or a large number of times, that we will get 1 upon 2 for head and 1 upon 2 for tail. This is what, when we are saying the probability for head is 1 upon 2 and probability for tail is 1 upon 2. And this is what we mean that the statistical property will not change. Now, these are some of the basic, or the better to say the characteristic or types of the random process that we are having. Now, the another one, which is what? This is the important one. So now the next one that we are having is Markov process. So what is Markov process? It is simply Markov process is also one of the kind of random process, one of the types of random process. So Markov process or random process, many time also called as random process with a certain restriction. So now let us try to understand it. So first, its application. So application, when I'm talking about random process, stochastic or Markov process, having many applications in engineering, science, economics, business, modeling, and many more. So basically, it is used to model a system that have a limited memory in their past. So a Markov process is what? It is a stochastic process where the system is having the limited memory about their past. Then such random process we are calling as a Markov process. Such stochastic or random process we are calling it as a Markov process. For example, gamble ruin problem. A gambler problem. So what exactly it is? The amount of money a gambler is having after n plus 1 games is only depend on the money that he is having after n games. Like whatever money a gambler is having at present, it only depends how much money he is having in the past. Past means what? Before this step. So this we call as a Markov process because it is having only limited amount of memory with it. Suppose at right now I am having, let it be 100 units of rupees. So in the next turn, that how much money I will have, it is only decided by this 100 units of rupees. It's not like what I am having previously or like in past. So this kind of situation we are calling as a Markov process, a special kind of random process, also known as a memory-less process. Also known as a memory-less process, or better to say, many situations where we don't have much past data of a thing, then by using Markov process, we can model that kind of phenomena and try to find out whatever the problem is needed. So another example, we can say population growth, like the number of individuals that we are having next year is depending on number of individuals that we are having at present. It's not what we are having at past. So many author also give the definition for random process as what? The future state, the future state of a process where the future state is only depending on the present state, not at the past stage, is called a Markov process or a memory-less process. It is used in, I have taken two example, population growth and gamble problem. It is also used in the prediction of the price of the stocks commodity, or like if I am having some market commodity is there, we want to predict its future price, then this process can also be used it. Moving ahead, for its mathematical definition, this is what the definition in the simple word. But if I'm talking about the proper mathematical definition, then what it is, let us try to understand. So a random process is called a Markov process. As random process already discussed, we are denoting it as xt, where t is the time index generally, but it may be any other indexed variable. We call it as a Markov process or first order Markov process. We'll discuss what we mean by order also. If suppose that we are having time variable as t0, t1, t2, tn, and corresponding random variable values xt0, xt1, xt2, xt n minus 1. So we will call this process as a Markov process if x of tn, the value of the random variable at time unit tn, is only depend on the value of the random variable at time unit n minus 1. It doesn't matter that what n minus 2, n minus 3 and else is given or not given, but we can find the value of the random variable x at a point tn if we know the information at the time t of n minus 1. So in terms of probability, we can say probability that x of t plus 1 is j. I'm taking j as a normal, means some specific value, not some specific, some general value. xt1, xt plus 1. You can say a, b, c, d, a1, a2, a3. We can take anything on it. I am taking it j. Given, this is the conditional probability, not the normal slash. So this is conditional probability. So the probability that x of t plus 1 is equals to j, given means what? When xt is I1, t minus 1 is I2, and then so on. X0 is I0 is equals to probability that x of t plus 1 equals to j given xt equal to I1. So if you see, it is same as here, it is given the past probability is also given. But since we are considering it as a Markov process, so it doesn't matter whether the past probability given or not. We can simply find the probability for a random variable at the time unit t plus 1 will becomes as a, if I am taking simple a, given the probability that x of t equal to b. So do not get confused by I1, I2, I3, is there, A, B, is there. These are only simple notation. You can take anything, A, B, C, D, A1, A2, A3. So this is what, if a probability distribution is following this result, that then that random process, we are calling it as a Markov process. We will call it as a Markov process, and we can find it by easily by using the conditional probability result, which comes out as equals to the probability x of t equals to b and is equals to the probability of their intersection. So if I am taking it as capital A and taking it as capital B, so it is what probability of A intersection B divided by probability of B, the normal definition of conditional probability. So by using this, we can find the probability. For example, suppose that at present a stock is trading at 100 rupees. Now, this is what, let it be the random variable xt, x equal to 2, it is 100. Now I am interested to know that what is the probability that the stock will trade at a price 101 at the time t plus 1. So by using this concept of random process, all the same time we can say we don't have any further past information, that what is the cost when tn minus 1 is there, like yesterday, day before yesterday, and in the same manner previously. If we didn't know that price of the stock commodity or stock price, so it doesn't matter. If we are using the Markov process, we can predict its future value on the basis of only today's value, which is 100 rupees. So today, what is the probability that it will get a value of this one? So this can be done by using the Markov process or a random process. So this is one example. Although if you search, there are many programs already run or already available online. Like if I give some example, like Opstra is there, Screener is there, Opstra, Option Trader software is also there. They're using these concepts. It's not only this concept, but along this, some other concept, because some other variable is also there which affect the price of a commodity. So these things can be used in those software also. So to explore these things, I suggest you try to understand the back-end working of those software also. Okay, moving ahead. Now, as in random variable, we have discussed that there are two kind of random variable. One is discrete random variable and another is the continuous random variable. Now, in random variable, there is only one input, but as I have already discussed, in random process, there are two. One is time index, another is a sample space. So now, on the basis of state space and time space, so this we will call as a time space. If time variable is there, this S we will call as a state space. So on the basis of the nature of this time space and state space, we further characterize a Markov process in four different categories. So now this table gives you the brief idea about those four things. So in this table, if you observe on side, I am taking a state space and another time I am taking a time space. Time space means time indexed space. So if now four options are there, time space may be discrete or continuous, as we have taken an example, continuous or discrete. And state space is also having two, continuous or discrete. Now, if we are having discrete state and discrete time, then such a Markov process we call as a discrete time Markov process or Markov chain. Now, what is Markov chain? Markov chain is nothing but if a state is discrete, then Markov process we call as a Markov chain. So if somewhere Markov chain is written, it means what? We are talking about a discrete state Markov process. A Markov process where states are discrete is known as a Markov chain. At the same time, if the time is continuous, then we will call it as a continuous time discrete space Markov process, or we can also call it as continuous time Markov process. Sorry, Markov chain. Because when I'm saying Markov chain, the word discrete is attached with state space directly. In the same manner, the third category is what? Discrete time and continuous state Markov process. Now here I am using the term Markov process because in Markov chain, the state space is discrete. So the total four category, if I am calling it, discrete time Markov chain, continuous time Markov chain. Now discrete time and continuous state Markov process and continuous time and continuous state Markov process. Now, as per the given situation, as per the given problem or given phenomena, we can decide that which one is suitable to model the given problem. Now, why we are discussing these things? Because by using these things, we can model some real situation, real phenomena, real world problem in terms of a mathematical model. And why it's needed? Because by using a mathematical model for that situation, then after we can use different methodology to predict or to find out the information or the output that we needed for a problem. Okay, so this is the classification for the Markov process. The same will also work for the stochastic process. So in a stochastic process also, we are having these four categories, but in case of Markov chain, we will use the word stochastic process. And there is nothing like stochastic chain. Be careful for it. There is nothing like stochastic chain Chain is used only in case of Markov. Okay, moving ahead. So after this, the next important thing that we are having is state transition probability matrix or transition state probability matrix. Now, what it is or what it gives, now on the basis of the given situation, on the basis of the given problem, we can construct a matrix. We can construct a matrix which gives you the different probability related to the given situation. If a matrix satisfying this thing, like it is giving the probability between the transition of different or various states, we call that as a state transition probability matrix or transition probability matrix, in short TPM. Using the simple concept of Markov process that we have discussed, like the probability Pij. What we mean by Pij? Pij means what? There is a state. If I give a name, it's 2i, and this is another state named j. So this is what moving from I to j. It gives is what the probability that xn plus 1 in the j state given that xn in the I state. That if we are in this state and moving to this state, so this is given as Pij. That is Pij is the probability of transition from ith state to jth state. So this, if I am writing it, this is the Pij value. Transition from ith state to jth state is the value of Pij, and it is nothing but the value of the probability. Another important point or the thing that we should take care for the TPM, what it says that the summation of all Pij on j is equals to 1. That means the sum of all the rows is 1. The sum of all the rows, the sum of all the rows of the matrix must be 1 as a simple constraint related to the probability. Now, this is transition probability matrix. One more thing that we are having related to this is known as the state transition diagram. Now, what we mean by state transition diagram? So, a state transition diagram is nothing but the representation or graphical or the diagrammatrical representation that how the various state in a problem is obtained. For example, like if I am taking two state in a system, like one is I, one is j, so let is this is Pij, and taking like this is some other probability, the probability moving from I to I, this is the probability moving from j to j. So this is what we call the state transition diagram. So a system is there which is having two state I, j. So I have mentioned all the possible things, the probability moving from I to j, the probability moving from j to I, the probability from I to I. That is, at time let it be t equal to a unit, the system is in I state. What is the probability that later on it will remain in I state? That is the probability from I to I. The same from j to j. That it as present, the system is in jth state, and now the probability that it will remain in jth state is this probability. So this diagram, a simple diagram that we have taken, we call it as a state transition diagram. State transition diagram. And it can be constructed and formulated on the basis of the given information or on the basis of the given data. So I just taken a simple example where only two states are there, I and j. But in general, it is not the case. There may be many number of states, 4, 5, 10, 100,000. So on that basis, we can generate a state transition diagram. And on the basis of a state transition diagram, a transition probability matrix can also be generated. And that the solution will give you the insight about the given problem. So now we have till now we have discussed about that what is a random variable. Then Type of random variable we have talked about. Some example we have taken on it. Then we have moved on state random process or stochastic process, taken some example on it. Then talked about the different things related to the stochastic process or random process. Another thing we have discussed about the Markov process and the terminology related to it. So till now, if there is any concern or doubt if you are having, you can ask for it. Any question or doubt if you are having?
Can you explain this once again? EIJ.
So now what happens? This is here there are two things. One is known as a state transition diagram, which also referred as the mathematical model for a given situation. Another is the transition state probability. In general, we can call them as a failure probability and repair probability. For example, we are having a machine, two machine system, machine A and machine B. So we are moving from functioning from machine A to machine B with this probability. If I am talking about this failure rate, so machine A is failed, suppose let it be probability is 0.2. I'm just taking it random. So there are 0.2, 20% chances that the system will moving from A to B. Presently, machine A is working. Now, when it fails, if I'm related it with the general standard terminology, if it is failed, the total load will be taken by machine B with the probability 0.2. For example, if I take one general example, like we are having electricity in standby mode in our homes, like main supply, and then is and at standby, it may be we are having some generators, inverter, or something else. So what happened? Suppose A means what? In this state, the main supply is going on. Now, main supply failed. Failed means electricity gone due to some short circuit or something else. With the probability, let it be, there are 20% chances that the main supply is stopped or disturbed. So the load will be shifted to your inverter or generator with the probability 0.2. So now we are on the standby unit. So now B2A, this we can call it as a repair rate or repair probability. So once standby unit take the load, generally the companies are having the maintenance teams or repairmen. So suppose that by the probability 0.7, this is repaired, and once again the process or the functioning comes out to the main supply. In the same manner, the probability that at right now we are with the main supply, and after as the time index moving on, we will be remain in the same. It may be some other probability. The same for B2B also other probability. So this is a simple example where two units is considered. One is power supply main unit. Another we are having standby unit. So standby generally denoted by, so standby unit. This is a simple system that we are having for electric supply in our home. Now, if all those probability means if I need to draw the state transition diagram, this is the state transition diagram. If I need to draw the transition probability matrix, then how it will be looks like, that is another concern. So since we are having two states, better to say. So the matrix representation will be a 2 by 2 matrix. Looks like this. On this side A, on this side B, on this side A, on this side B, and we will move like this. So this is what our transition probability matrix or TPM. So A to A. What this entry reflect? The probability that the system is working in the same state A. What this denote? The probability that presently we are in state A but move to state B. Now this entry is B2A and this entry is B2B. So all these entries we can put it in the matrix on the basis of the data or information. This is known as the transition probability matrix and this is known as the state transition diagram or a diagram which represents the relation between the various states of a problem. Yes, is there any other concern?
No, thank you.
Okay. Anyone else? Okay, so if no concern, moving further, we will take some journal example or some problems so that you will get more clarity. Chaliye. So this is one example. I request to all of you try to read it and try to understand it. For next 30 seconds to 1 minute, try to read it and try to understand it. At last, they are asking that we need to draw a transition diagram, that is the transition state diagram for this problem, as well as we need to find the transition probability matrix for it. So try to read it and then try to understand it.
Here, is there three states involved in this case?
So exactly, like we can see there are three states or this situation is having three category or state. Actually give a person raise hand. So one state we can say upper class family, another is lower class and middle class. So as in the previous example, we are having A and B, only two. Here we are having three state, upper class, middle class, and the third one is I think lower class. So these three state is given to us and also some more information is given. So on that basis, we will try to draw a state transition diagram as well as a transition probability matrix. So we can draw it as like this. So I am taking it as upper class. This state is representing that an individual in upper class. Another we can make a lower class and another we can take a middle class. So this circular notation is representing the three states for the situation lower, upper and middle. Now let us see what else given to us. So what is given, try to read it first. Yes. So assume that the pupils in a particular society can be classified as belonging to upper class. So either an individual in upper class or in middle class or in lower class. Now membership in any class is inherited in the following manner. That means if a person raised in upper class family, he or she will have an upper class family with a probability 0.7. What it means, if suppose that a person is born in upper class family, so it will remain in upper class family with the probability 0.7. It means upper class to upper class, this probability is given as 0.7. In the same manner, what else is given? Let us move on. A middle class to middle class, that a person born in middle class and will retain middle class is 0.2 and lower class to lower class is 0.1. So this is how, let me move on to the diagram. So this is lower class to lower class probability and this is middle class to middle class probability. So lower class is given 0.1. So this probability is 0.1 and this probability is 0.2. This is only the individual probability. Now let us proceed. What else is given in the question? Now, similarly, given a person raised in middle class family, he will have upper class. Have I write it correctly? Point 2 and point 1, correct. So now what next? It is given that if an individual is in middle class, then he will move on to upper class with the probability 1. So middle to upper is 1. Where is middle? So this is middle and this is upper. So the probability of this thing is 0.1. So the probability for this is 0.1. Now what else given? Let us read the question. Middle class family, what I write, similarly, given that a person raised in middle class family, he will have upper class with this. Middle class family with the probability 0.6. So, given a person is in middle class family, he will in upper class 0.1, middle class family with the probability 0.6. And to middle class, the probability is 0.6. The rest thing, a lower class family, probability 0.3. Finally, given that a person raised in lower class family, let me read it again, what it is given. Given a person raised in upper class family will have in upper class 0.7, middle class 0.2. Okay. So what it is given, it is correct. So the relation I need to reframe. Firstly given from upper class to upper, then upper to lower, and then upper to middle. These things are given. So means the data is given one by one. So I need to reframe it. If you understand, you can draw this graph or can draw this transition probability matrix. Sorry, not matrix, the diagram. So upper to upper, if given that a person he will be upper class 0.7, upper to upper is 0.7. Then upper to middle 2 and upper to lower 1. Upper to middle, upper to middle, this is upper to middle, it is given as 0.2, and upper to lower, so this is given as 1. So this is one information. Similarly, given a person raised in middle class, so middle class, he or she will be have upper class with 0.1 and middle class 0.6. Upper class 0.1. So now we will conduct middle to upper. So this is middle, this is upper. So middle to upper, it is given is 0.1. In the same manner, middle to upper 0.1, middle class family with 0.6, as it is 0.6. So this is 0.6, as it is 0.6, and 0.3. Middle to lower is 0.3. So middle to lower is 0.3. Finally, given a person raised in lower class family will be middle class 0.3, lower class 0.7, middle class 0.3. So this is also 0.3. So this is 0.3. Middle class 0.3 with and lower class with 0.7. So it is lower class with 0.7. So make it 0.7. So this is given as 0.7. And lower to upper class, how much it is given? Lower to upper class, it is given or not?
Not given.
So not given, we will not write it, no matter. So middle 0.3, lower class member. Find the state transition diagram. So this is what we call the state transition diagram for the situation. So as per the information, you can see this diagram, what it represents. It represents the different state for the given problem. And we will connect also the arrow matters. Huh? So upper, low, upper class to lower class is 0.1. So we can't say lower to upper is also 0.1 because it is not given. Na? So whatever given, that direction is also matters. So this is known as the state transition diagram for the situation. On the same manner, we can also make a state transition probability matrix. So TPM, transition probability matrix. So three state, upper class, lower class, middle class, and on the other side also upper class, lower class, and middle class. So as I already told you, we will move like this. So probability upper to upper is 0.7, upper to lower, upper to upper is 0.7, then upper to lower is 0.1, upper to middle is 0.2. So lower to upper, lower, so this is lower, this is upper, not given. Lower to lower is 0.7, and then lower to middle is 0.1. In the same manner, we can put rest of the entries. So this matrix we call the transition probability matrix. So for this situation, we have make two things. One is the transition probability matrix and another is transition state diagram.
So lower to middle is 0.3.
Lower to middle is 0.3. Okay. So whatever is given, we will put it over here. So this is how we can model a situation in terms of a state transition diagram as well as a
So middle to lower 0.3.
middle to lower is, so whatever it is given, put it over here, this matrix, no problem. So this is how we can make a transition state diagram and transition state probability. Now what happens since we are in the initial phase of modeling through a Markov process, so the probability is given, but most of the time in place of probability a data values is given, a data set is given. So first we need to use that data set to find the probability, and also by using the given data set we need to check that from which state to which state the process or the transition is possible or not. So on that basis, we can make the state transition diagram, and this will give you the transition probability matrix. Now, after making the state transition diagram, we can use a different methodology to find whatever the question is asking. Asking means it's not about this is what we are doing. We are only representing the given set of information in terms of a transition probability matrix as well as in terms of a state transition diagram. We are not doing anything else. But it's not as simple as it looks like in this problem in journal or when you are moving to write some publication or research paper. For that, first you need to identify some problems. Then you need to decide the different possible states that a system may have, and after that you will decide that what are the possible transitions are there from one state to another state. Then generally direct probability is not given. If I am talking about some production system, some industrial system, over there generally the failure probability and repair probability or failure rate or repair rate will be given to us. We will put it over there, and on this basis a system of differential equation, intro differential equation, partial differential equation or normal linear equation can be generated, and the solution of those system of equation will suggest you the insight about the given problem. So if exact solution is not possible, we will proceed for approximate solution as already discussed in offline mode, that if exact is not there, how to proceed for approximate. If exact is there, so that is the best thing. We can directly find the exact solution. Now, what I am saying solution or what we mean by solution over here, it may be any information related to the given problem. For example, suppose as I have taken an example of production, the first one like electricity mains and standby. So in this situation, a person or an individual is maybe interested to find that what is the probability that there is no power cut, no power shutdown in the home. Power shutdown means what? Main is not working as well as standby is not working, or how the reliability of the system is there. Means many parameters are there. We are interested to find the how much system is reliable, available, and another thing, if we are dealing with a production system, so we may be interested that what is the expected revenue from the system, expected profit from the system by including some more variable in the process in the system. So these are some of the real life applications that we are having related to the stochastic process, Markov process, random process in the real life scenarios. If there is any concern, you can ask for it. Okay, so if no concern, let us move or proceed further. Now in question number 2, what they are talking about, a state transition diagram we need to make, and this is a transition probability matrix is given. So matrix is given and we need to make a state transition diagram. So as a reference of the previous example, from a data we can make a transition diagram as well as transition probability matrix. But here the data is not given, no problem. A transition probability matrix is given, and by using it, we can make a transition state diagram. There is a correction in this transition probability matrix. Can anyone identify that? Is there any correction or
3.25.
correct?
3.25.
Correct. As it is a probability matrix, so none of the entry is greater than 3. So this is a small correction, and rest of them it's okay, no problem. One more way to check a transition probability matrix correctness, the sum of each row should be 1.
Yes.
The sum of each row should be 1. So if something correction is there, we can correct it as per the rule or as per the thing that we have discussed. So this should be how much? 5, 2, 5. So this will be only 0.25.
25.
Correct, correct. So let us make it as 0.25. Now try to make a transition diagram from it. Within next 2-3 minutes, try to make a transition diagram from it. So total state we are having 1, 2, 3, 4. As it is a 4x4 matrix, 4 state. We can give the name as ABCD or 1, 2, 3, 4. As you like. So I am taking 1, 2, 3, 4. So as we are moving like this, 1 to 1, the probability is 0.5 and 1 to 4 is 0.5. In the same manner, the second one, so it is 2 to 1. So 2 to 1 is 0.5. 2 to 2 is 0.5. So this is 2 to 2, this is 0.5. No further correction. So 3 to 1, 3 to 1. So this is 3 to 1, 0.25. 3 to 2, 3 to 3 is 0.5. So 3 to 3.5. 3 to 4, 0.25. 0.25. Now 4 to 1, 0, 4 to 2. 4 to 2, so this is 4 to 2, 0.5. 4 to 3. 4 to 3, so this is 4 to 3, 0.25. Do take care for the direction also. And 4 to 4, 0.25. So this is what, or this is how the state transition diagram looks like for a problem whose transition probability matrix is given. I hope there is no concern in this example. If any doubt or concern, do let me know. So should we proceed further? Waiting for your response.
Yes, sir.
Okay. Moving ahead. Taking one more example. Example number 3. So determine the missing element in this transition probability matrix. So here some values, or better to say some entries of the matrix is given as unknown x. The question is asking find the value of x. So quite simple, as we have discussed that sum of the each row must be 1. So if I'm doing for the first row, so x plus 1 upon 3 plus 1 upon 3 plus 1 upon 3 must be 1. We can find x from here for the first row. For the second row, so 1 upon 10 plus x plus 1 upon 5 plus 2 upon 5 equals to 1. You can find x for the second row. In the same manner, for the third row, it must be 0 because the sum is already 1. For third row, you can also find this is sum. So these two must be 0. This is also 0. Here, how much it is? So this will be somewhat how much? 5, 2 plus 3, 3 upon 5, 6, 7 upon 10. 1 minus 7 upon 10 will be 3 upon 10, I think. So this will be somewhat 3 upon 10. The first one will be 0. So do cross check your values. Are you able to find these values? Yes, should I proceed?
Yes, sir.
Okay. Taking one or two more example. So this is also one of the example. Now what happen? A transition diagram is given. We need to find the transition probability matrix. Quite simple. So skipping this question. Yeah, question number 5. This is interesting one. Question number 5. So it is also known as a gambler problem. Okay, try to read it and try to understand it. Smith is in jail and has $3. So one individual whose name is suggested as Smith and he or she is having $3. He can get out on the bail if he has $8. Presently 3, but he need 8 to move out from the jail. So a guard is agrees to make a series of bets with him. So Smith, if Smith bet $1 means $1, he wins $1. Means if he bet $3, he will win $3. With the probability 0.4 for winning, and 0.6 for losing. So if all the $3 put it on bet, he will get $6 with the probability 0.4, and he will get 0 for all the $3 will be finished with the probability 0.6. Now we need to find the probability, or better to say, we need to find the probability that we will comes out from the JD. With the condition, if we start with the $1 bet each time, timid strategy, we also call it as timid. The second, he bets each time as much as possible, but not more than the necessary to bring him fortune up to $8. Means the game must be ended either at 8 or 0. The game will be stopped if we lost all the things, that is 0, or if he has total $8. So now by taking this consideration, we need to, or we will try to generate a transition state diagram as well as the transition probability matrix for this situation. So let us try to start the problem. So we are in the state 1. So I am drawing it for part A, $1 each. So here we will start with that $1 each. So this is, let it be state A, or I am putting it as $1. So with 4 probability, 0.4 probability, converted to how much? Presently, better to write the dollar that is having $3 I am taking as a state name. So 0.4 probability that it comes out to be how much dollar? $4. If $1 is bet. If you are getting confused that 3, 4, we can write the state name as A1, A2, A3. So I am taking first state as A1, A2. So in A1 state, he is having $3, A2 state $4 if he wins. But on the same time, if he lost, let us make this state as A minus 1, only notation. So now he will have $2 with him. $2 with him. In the same time, we will proceed further to complete this strategy. So one more time, let us make it as A3. So now $5 he will have. On the same time, if loss, then after this 0.4, after this I am making it as once again A4. So he will have $6 with the probability this 0.4. Then next A5. Now he will have with 4 probability $7. Now after A5, I need to move on to one more state, A6, with the probability 0.4, and now he is having $8. So no further bet is allowed. The probability from A6 to A6 will be 1. Do take care of this thing. A6 to A6, 1. But we are only considering the winning probability. Now failure is also there. So let us take the failure also. From here, if failed, $7. From here, if failed, $6. From here, if failed, $6. Since I am considering $1 with each time, so only movement is from immediate states also. $2 I am not considering, 3 I am not considering. We are only considering only $1 bit. From here, 0.6. From here, 0.6. Here, 0.6. Also, like on the back side, how much possible? Until unless 0 is there. So from here, we can proceed to A of -2 also. Do not get confused, -1, -2, these are only the notation. So 0.6, now he will have only $1. One more time, A of -3, 0.6. So how many dollars he will have? 0. So on backend, A -3 will be the last state. Probability from A3 to A3 itself is 1. A3 to A3 itself having $0 will have $0. So it's 1. Now this probability will be 0.4. This will be 0.4. This will also be 0.4. So this is what the transition state diagram that we are having for this situation. This is also known as the gambler problem. As you can see, at every state almost, there are some birth of new state and some death of the states. So this process is also known as Markov birth-death process. This is also known as Markov birth-death process. See it carefully. If having any concern, you can ask for it. The same you can make by starting $2 bit, $3 bit. Can I start with $4 bit? Obviously no, because the only $3 is available with Smith. So it's not possible that we can move on with $4 bits. So this is what we are having Markov death worth process, or also known as the state transition diagram for this problem. Now they are also asking which strategy gives Smith the better chance of getting out from the jail. For this, we need to calculate the probability for each transition diagram. And which one is higher? That will be the solution or the suggested process for bidding. See it for next 1 minute. If having any concern, ask for it. Otherwise, we'll proceed further. Concern? Waiting for your response.
Yes, sir, we can go ahead.
Okay. So this is all about the random process and stochastic process. Time is almost over, only 10 minutes left over. So I will not start the new thing. So the rest of the thing we will discuss tomorrow class. Tomorrow we are also having a class. So if no concern is there, I'm going to just stop sharing and closing this meeting. So I hope you understand the concept and understand how it can be implemented in the real life situation and problem. If you are having further queries, you can please directly write to me or directly come for the discussion in the campus. If no concern is there from your side, That's all from my side. Thank you everyone for joining the session.
Thank you, sir. Thank you.
Thank you, sir.
Thank you, sir.